Before I begin, I'd like to thank HumTech for accommodating me in my absence. I regretfully won't be able to join the conference today, but I appreciate the chance to present remotely. So I am an undergraduate student at Penn State University and part of the Humanitarian Engineering and Social Entrepreneurship, or HESE, program, which works on sustainable development ventures throughout the world. Today I'm going to be talking to you about affordable greenhouses, which are one of our sustainable development ventures, and how they are a climate-smart, technologically based solution to fighting food and water insecurity throughout the world. More specifically, I'm going to be talking to you about how greenhouses save water and how understanding the modes by which they save water can help us improve their water savings potential. So, food and water insecurity are a big problem in many areas of the world, and most notably in sub-Saharan Africa, where much of the region is water scarce. And water scarcity ties in directly to food security issues, because agriculture consumes about 80% of the region's water in sub-Saharan Africa. And climate change threatens to further exacerbate these food and water challenges by threatening the world's water reserves in these areas and increasing dry spells and desertification. And so one very promising technological solution to these challenges are greenhouses. The problem with greenhouses in sub-Saharan Africa is that they can run up to about $6,000 and are therefore inaccessible to smallholder farmers living on $2 per day, or more designed for large-scale commercial farmers and larger organizations. So we at HESE designed an affordable greenhouse for smallholder farmers, large-scale farmers, and anyone in between. These greenhouses are made from an imported plastic material and otherwise all locally sourced materials, and cost a fraction of what the competition costs, all while delivering the same year-round growth benefits and reducing water, all the same as a regular greenhouse. And so these greenhouses, we have over 200 of them throughout sub-Saharan Africa. They can all be built by 2 carpenters in 2 days. I'll walk you through a little bit of the process. So on day 1, 2 trained carpenters would arrive on a cleared plot of land. They would dig holes and build the frame on day 1. On day 2, they would install the plastic glazing material and run through with the farmer a farmer education tool that we at HESE designed on one of our Kindles. Now, the farmer education tool will emphasize among other things, it will emphasize different use cases for the greenhouse. One of which is pretty straightforward. It's seed to harvest. So planting seeds in a bed or in a nursery and either transplanting them directly into the beds or maintaining them until maturity. Alternatively, some farmers have been known to use our greenhouses and take advantage of the high germination rates inside of the greenhouse to grow seedlings and transplant them into their open air farm so they can have more of them more spread out across the land. Alternatively, they can, instead of transplanting them, they can directly sell those seedlings and turn around and just grow another batch of seedlings with a fairly quick turnover, as the seedling crop cycle is relatively short. Now, these greenhouses can be sold in one of 2 ways depending on the customer. So for a larger organization, like a large-scale commercial farmer or an academic institution or an NGO, we might sell them as a direct asset sale where the full payment is made up front. But to access smallholder farmers and women's cooperatives, we might sell on a cost recovery basis system where installments are paid for every successful growing cycle. And these greenhouses ultimately make money once they're paid off, mostly because of the increased yield potential. So our smallholder farmers, for instance, have achieved on average about a factor of 3 times increase in yields, while women's groups have about a factor of 5% increased yields, and commercial farmers a factor of 10. And now we have, as I mentioned, over 200 of these greenhouses throughout sub-Saharan Africa, so I'll give you a little timeline of where we've been so far. First, in 2012, we licensed our greenhouse technology to Mavuno greenhouses in Kenya, which continues to this day to operate independently. Similarly, in Cameroon in 2013, we licensed our technology to Greenhouse Ventures Limited, which also continues to operate independently and produce greenhouses on their own. And more recently, in 2014, we partnered with World Hope International to form Grow Greenhouses and received a $500,000 Saving Water for Food grant from USAID, which enabled us to build greenhouses in Mozambique and in Sierra Leone, where much of our efforts today have been concentrated. And even more recently, in the last few weeks actually, we received a grant from the State Department to build 10 greenhouses in Cambodia, the construction of which will start this summer. Now, when we received the Saving Water for Food grant, we started to have to keep track and record how much water we are saving as compared to open-air farms. And this really got us interested in how exactly greenhouses are saving water. And so we developed a methodology that says that greenhouses are conserving water through 4 distinct modes. All these modes work in conjunction with each other inside of the greenhouse to render them an effective water savings technology. And all of them can also be modeled to predict a greenhouse's water savings potential. So I'm going to walk through each of these modes and what they mean and how we model them. So first, reduced evapotranspiration. This is probably the best documented mode of greenhouse water savings. It basically means that crops grown inside of a greenhouse are less likely to lose water through evaporation and transpiration because of the moist environment inside of the greenhouse. Now, this can be calculated through the Penman-Monteith equation, which, although it looks relatively intimidating and large, is really just a function of temperature, relative humidity, and wind speed under a few simplifying assumptions. And all of these 3 parameters can be measured on a relatively cheap weather station, and also can be found online to retrieve long-term trends in evapotranspiration differences between the greenhouse and the open air, such as the plot on the screen from greenhouses in Mozambique. And so this percent difference in evapotranspiration effectively describes the water saved through reduced evapotranspiration rates. Second, we have closer crop spacing. Greenhouses can support more dense arrangements of crops because the greenhouse plastic diffuses sunlight to different parts of the plant. So they can be spaced as close as 30 centimeters together depending on the plant. And this mode saves water because it reduces the water wasted through manual irrigation. And so we would calculate more water essentially goes to the root zone rather than to the surrounding soil where it is wasted. And so to calculate the water saved from closer crop spacing, we would essentially normalize the area of the open air plot compared to the greenhouse plot and calculate the reduction in area into the water usage requirements. Similarly, drip irrigation saves water by reducing water waste as the distribution tubing applies water directly to the root zone of a plant and can reduce water by up to 50% according to the World Bank. Some of our greenhouses have drip irrigation and can save a tremendous amount of water this way. And fourth, we have the fact that greenhouses can reduce the length of a crop cycle. And they do this by accelerating plant growth as more light reaches the different parts of the plant throughout the day, similar to the reasoning behind the closer crop spacing, dense arrangements of crops. So a shorter crop cycle means fewer days spent watering crops and fewer days losing water through evapotranspiration. And so it is one of our water savings modes and can be calculated as compared to open air plots by normalizing the crop cycle time between the two. So all of these 4 modes work in conjunction to conserve water, but it is unclear how much actually should be attributed to each one, because there are certainly confounding variables present. But in our model that we just described, we calculated that in Mozambique, our average greenhouses use 62% less water, and in Sierra Leone, 32% less water. This difference can be attributed to climate, for one. Mozambique experiences for most of the year a windier and drier climate than in Sierra Leone. And also, our Mozambican farmers were using the area in their greenhouse more efficiently and spacing crops more closely together. So we recognize that in order to develop a holistic and accurate model of greenhouse water savings, we also need to account for some confounding factors, some of which we maybe aren't even considering at the time. For instance, our current model treats the reduced crop cycle time as just a proportional difference to the open air crop cycle time, when in actuality, a reduced crop cycle in the greenhouse may require more water for the accelerated plant growth, something that is not accounted for and can really only be discoverable through experimental data. And so currently in Sierra Leone, we are collecting data on our operational greenhouse, just asking farmers how much water they use per week in the open air and in the greenhouse, taking into account things like crop type, crop spacing, and the crop cycle length, also measuring water data. Also measuring weather data from our weather stations. All of this is to attempt to provide insight into how these water savings modes interact in order to refine our model and make it more accurate in predicting greenhouse water savings. All of which so that we can better understand how greenhouses save water and use this information to maximize a greenhouse's water savings potential. And with this, I would like to once again thank HumTech for allowing me to present remotely. I'd also like to thank all of our partners. I hope to be available on Skype for the next few minutes to answer any questions, but if something happens that does not happen, I would happily answer any questions via email. Thank you all for your time.